Hi, my name is Aleksandra Shuianova, and today I want to present my thesis titled Kinship Verification Between Two People by Photos. So, first, I want to present my table of contents. The following slides will follow this structure. I will start with the introduction, where I will describe what kinship verification involves and the areas in which it can be possibly applied. Next, I will review previous works on this topic and discuss their shortcomings. After that, I will outline the objectives I set in my thesis. Then I will describe the data set used for training the models. I will also briefly outline the architecture of the chosen models as well as the technologies used. Following that, I will walk through the development process of my proof of concept application step by step. Finally, I will present the results of the work done along with their evaluation and conclusions. In computer vision, kinship recognition is the task of training a machine to recognize genetically related and unrelated people based on features extracted from digital images. An important component for research in the field of kinship verification is a database with photographs of people's faces and descriptions of their kinship. Recently, kinship verification has attracted the interest of researchers and is actively used in various fields. This is due to the remarkable progress of deep learning in extracting deep features for face image analysis over the past 10 years, particularly in kinship verification. Besides, there is a wide range of applications for kinship verification. For example, in the fields of anthropology and genetics, kinship verification can help study hereditary characteristics that unite close relatives. Additionally, kinship verification can be applied in social security to find relatives of a found child. Furthermore, kinship verification can be used in smart home systems for recognizing family members' faces and in other applications related to personalization in the Internet of Things. So, when looking at recent research in kinship verification, a trend towards the use of deep neural networks can be noted. For example, in a 2019 study, the author attempted to predict the kinship of two individuals based on photographs of their faces using the Families in the Wild dataset and the ResNet-50 neural networks. For training the neural network, a pair of images was fed into the input, and the output was 1 if they were relatives and 0 if they were not. Basically, the model learned to analyze images based on some quantitative characteristics, such as eye color, head shape, forehead height, looking for similarities in images. This can lead to the fact that simply look-alike people who are not relatives will be identified by the model as relatives, which is wrong. If the algorithm had somehow also analyzed family members, then such an error could have been avoided, taking into account, for example, that for a particular family, it's not just one eye color or hair color are important, but the inherited shape of the nose, for example. In another study from 2013, the Family 101 database divided into families was used. Unlike the previous study, this one included the analysis of the appearance of each family member. The goal was to determine which family a person belongs to. For this, the researchers used an algorithm that reconstructed the query face from a sparse set of samples among the candidate families, as presented on the slide. The resulting faces were compared with the input face, and the face with the least difference indicated that its parts most likely belonged to the relatives of the person being sought, thus identifying the family. However, despite the interesting concept, this study didn't use modern machine learning algorithms, which could make an algorithm more efficient and provide greater accuracy. The aim of this thesis is to evaluate the feasibility of using convolutional neural networks to determine kinship between two individuals based on their photographs with consideration of family affiliation. In this work, a proof of concept application was developed. The program is based on CNN models, which were trained on different data sets with photographs and then tested for evaluation of its accuracies. Based on the test results, I was comparing models and selected the one that performed the best. Additionally, I assessed how the quality of the data set impacts the model accuracy. The Family 101 dataset was selected as the training data for the models. It is the first large-scale dataset of families that includes multiple generations. It includes 206 families, each with 3 to 9 family members. The picture on the slide shows one of the families from the dataset, the Kennedy family, with a 3-generation family tree and 48 images of one family member, Caroline Kennedy. All images are stored in JPEG format with a fixed size. The structure of archive of dataset you can see on slide. The application for kinship verification was developed by using Python programming language in Google Colab. I also used GPU to accelerate model training. The following frameworks and libraries were utilized for development: PyTorch, Pandas, NumPy, Matplotlib, Sklearn. Between the classical machine learning methods such as support vector machines, SVM, key nearest neighbors, decision trees, and deep learning methods based on CNNs, I chose the second one. While the KNN algorithm requires manual feature extraction from the image, which is time consuming, CNNs perform this process automatically and more accurately. Kinship verification requires determining as many features as possible, since the dataset will contain people of different ages and photographs from different times. This is why convolutional neural networks are best suited for solving this problem. In this work, the ResNet-50 and AlexNet CNN models were used. Now I'm going to briefly describe the architectures of both CNNs. ResNet-50 is CNN architecture that belongs to the residual networks family, a series of models designed to address the challenges associated with training deep neural networks. ResNet-50 is renowned for its depth and efficiency in image classification tests. ResNet architectures come in various depths, such as ResNet 18, ResNet 32, and so forth, with ResNet 50 being a mid-sized variant. The primary problem ResNet solved was the degradation problem in deep neural networks. As networks become deeper, their accuracy saturates and then degrades rapidly. This degradation is not caused by overfitting, but rather the difficulty of optimizing the training process. ResNet solves this problem using residual blocks that allow for the direct flow of information through the skip connections, mitigating the vanishing gradient problem. The AlexNet architecture is shown on this slide. It contains 5 convolutional layers and 3 fully connected layers. ReLU is applied after each convolutional and fully connected layer. The dropout is applied before the first and second fully connected layers. The network contains 62 million parameters and spans 1 billion calculations in a forward pass. As an activation function, ReLU is used instead of arctangent to add nonlinearity to the model. Due to this, with the same accuracy of the method, the speed becomes 6 times faster. Using dropout instead of regularization solves the problem of overfitting. Well, I divided the development of the application into 5 key steps. The first step is a dataset preprocessing, which involves selecting families for the training and test datasets. I aim to choose families with diverse characteristics, some with more photos, some with fewer, some with higher quality, and some with lower quality. Also, I removed some photos that I consider unsuitable, either due to very poor quality or improper angles. As a result, I selected 11 families. The second step involved deciding which family members would remain in the training set and which would be included in the test set. I follow the principle of selecting the youngest family members for the test set, as they would have connections with every other family member. As a result, I ended up with 960 photos in the training set and 131 photos in the test set. In the third step, I developed an algorithm that generates train CSV and test CSV files, where the first column contains the file name of a person's photo, and the second column contains the label of the family number they belong to. Subsequently, I create data loaders from the collected CSV files to train the models. In the first step, I define the model and choose which optimizer and loss function I will use. For both models, AlexNet and ResNet, I used cross-entropy loss as the loss function because it's suitable for multi-class classification, as in my case. As the optimizer, I chose the ADAM optimizer. Finally, in the fifth step, I develop an algorithm that includes training and testing the model, collecting the results of the loss function, and evaluating the accuracy on the both datasets. During training, the model receives a batch of images with a predetermined size of 15 photos rather than just a single labeled image at a time. Let's look at the results of ResNet 50 model that was trained on the first version of datasets. Analyzing the confusion matrix yields the following conclusions. The tested Bush and Kaziraki were correctly classified into their families in 52 and 41% of cases, respectively. The model did the best job identifying them. However, in 46% of the cases, Kaziraki was misclassified into the Bush family. It's easy to conclude that the large number of Bush family photos significantly influenced the accuracy of correctly classifying them into their families. However, such an uneven distribution of photos per family negatively impacts the accuracy of classifying members of other families, often misclassifying them as Bush family members. In the case of the Kaziraki family, it can be assumed that the quality of the photos positively affected the accuracy of classifying the tested Kaziraki member into her family. In the training and test datasets, all Kaziraki family photos are in color, clear, and with faces looking straight ahead. The worst classified were Hoover, Wilson, Rockefeller, Clinton, and Roosevelt. It's assumed that their poor results were influenced by the low number of photos for the tested individuals. The previous train and test sets were edited based on the results of the previous testing. In the Hoover family, the family member being tested with only one photo was replaced by another with 17 photos. In the Clinton family, 9 photos of Chelsea Clinton were added to the test dataset, along with several new younger photos of Bill and Hillary Clinton in the training set. In the Rockefeller family, the previous test member was replaced due to having a beard, which could affect classification, in my opinion. Additionally, new photos of mother were added to the training set. The analysis of the resulting metrics show improved classification accuracy for the Kaziraki family, with 68% of photos correctly identified. However, the number of falsely classified Kaziragi has increased from 13 to 41. The number of false classifications for the Bush family decreased from 52 to 11. Previously, Bush was mistakenly classified as Kaziraki in 5 cases and Kaziraki as Bush in 9 cases. Now, Bush is misclassified as Kaziraki in 8 cases, while the misclassification of Kaziraki as Bush remains at 9 cases. Additionally, the new Rockefeller test subject was incorrectly classified as Kaziraki in all instances, indicating that replacing the Rockefeller subject worsened the model's accuracy. This decline may be due to the lower quality of the Rockefeller training data, potentially causing other test subjects to be misclassified as Kaziraki as well. Now let's look at the results of the AlexNet model that was trained on the second version of datasets. The confusion matrix indicates that the model tends to misclassify other classes as belonging to the Kaziraki family. This behavior likely results from an imbalance in the dataset's quality across the different classes. The Kaziraki family photos are high quality and colorful, which helps the model identify this class more accurately. Despite the Bush family having a large number of photos, the lower image quality affects classification accuracy. The more complex AlexNet model compared to ResNet 50 benefits more from high-quality images, as it can extract more features, highlighting the impact of image quality on performance. I also tested the models on 2 selected people from the Kaziraki and Bush families, Charlotte and George Prescott. We can see that the most of Charlotte's photos are correctly identified as Kaziraki, as well as the most of George's photos. The model was successful because it revealed that the test subjects were not from the same family, therefore not relatives, which is true. Now let's look at the results of AlexNet model. We can see that most of Charlotte's photos are correctly identified as Kaziraki, most of George's photos are correctly identified as Bush. The model is successful because it revealed that the test subjects are not from the same family, therefore are not relatives, which is true. As a result of the work done, a proof of concept application was developed to solve the kinship verification problem. The application uses deep neural network models. The selection is performed between two CNN architectures, ResNet 15 and AlexNet. During development, three models were trained on two different datasets: ResNet 50 version 1, ResNet 50 version 2, and AlexNet version 2. Version means the version of dataset. The ResNet 15 version 1 model demonstrated the best performance among the tested models. Although ResNet 15 version 1 and ResNet 50 version 2 had similar loss and accuracy values, a detailed analysis of their confusion matrices showed that ResNet 50 version 1 was better at correctly classifying the Bush, Kaziraki, Truman, and Reagan families. Additionally, ResNet 50 version 1 errors were more evenly distributed across all classes, while ResNet 50 version 2 had a much higher misclassification rate for the Kaziraki family. The AlexNet version 2 model, with its more complex architecture, is more sensitive to image quality, extracting more features from high-quality photos, such as those of the Kaziraki family. This sensitivity led to higher errors with lower quality images from other families, highlighting that photo quality rather than quantity is crucial in kinship verification. Quality in this context refers to the absence of noise in photos. The ResNet 50 version 1 model also showed that a significant imbalance in the number of photos across families negatively affects performance, as seen with the Bush family, which had a higher percentage of false classifications due to the large number of photos. In conclusion, among the three models, ResNet 50 version 1 was the most effective in solving the kinship verification problem, demonstrated that CNN models can successfully determine kinship between individuals based on photos with careful consideration of image quality and class balance.